Welcome, everybody. Thanks so much for coming to my talk today. This is building HTTP proxies on autoscaling systems for Kubernetes. I couldn't fit the whole title on the slide, so I just shortened it to that. Anyway, I'm Aaron. I work for Microsoft as a cloud developer advocate inside of Azure. I put my Twitter handle there on the slide, and you can also reach me at that handle pretty much all over the internet, GitHub, Twitch, and so on and so forth. So feel free to reach out. I'm more than happy to talk about this topic. You may have also seen me around doing a lot of things with modules and module proxies as well. I'm happy to talk about that too. So I just want to set the stage here. This talk came out of some work that I had been doing and have been doing on Kubernetes, doing HTTP scaling and routing for autoscaling systems. So I'll have a link at the end of the talk to the KEDA project, which is this specific technology that I'm building all of this autoscaling and proxying on top of. But this specific content that you'll see today came out from the fact that I went into building this system expecting the facilities that Go provides for HTTP and doing reverse proxying inside of the standard library. I was expecting that to be fairly robust and to be able to solve all the problems I needed to solve. Now, even being around Kubernetes for a long time, I still almost always underestimate how many edge cases there are and how challenging it is to build a truly robust and resilient system on top of Kubernetes. So really anything that needs to talk to something else in the cluster or anything that needs to handle state, you really do have to handle a lot of edge cases. You really do have to test quite a bit to build something that's truly resilient. And this was no exception. So I'm really excited to share this with you today because there really are a lot of learnings in here. And while you're watching this and you're seeing the code, try to remember that all of this came from sort of pain that I encountered. And I'm really excited to share that with you today. So let's get into it. The approximate architecture of this thing composes of 3 services. So there is something that we call the origin, there's a proxy, and a scaler. Now we'll go into more detail about each shortly, but the short description of each thing is the origin is the piece that we're trying to proxy to. Okay, so that's the only piece that we don't control. A user will write the code, they'll run the origin on Kubernetes, and this is applicable to other systems too. So they'll write the code and host it wherever the proxy is running. The HTTP server will be accessible from only inside of the cluster or any closed system that you're running on. Okay, so the origin is not served to the public internet or to the wider outside of the cluster environment. The proxy is then what you put in front of the origin. It serves as an ingress, so it terminates SSL, it accepts incoming requests, and then of course the point of the proxy then is to route those requests to the origin or origin replicas, origins, if you will. Inside of a system like Kubernetes, when you're auto-scaling the origin, in order to be robust, I mentioned it has to do a lot more, and we're going to dive into that today. But what the proxy essentially needs to do is accept those requests coming in, identify where to send the requests in the backend. If there is nowhere to send them, hold on to those requests. Trigger some event to get the origin scaled up to create a place to forward that request. And then once the origin is ready and serving, the proxy then forwards the request back to the origin and then expects a response that it can then forward down to the initial client that made the request. So the proxy has quite a few challenges there that we'll dive into. And one of the challenges is it needs to talk to a third component called a scaler. And the scaler is what we call a controller or an operator in Kubernetes speak. And it runs in the background and it attempts to automatically scale the origin up and down, depending on some inputs. Generally speaking, the scaler scales up and down depending on some metrics that it takes from the proxy and potentially other places. But the goal of it is to scale up when it expects that there is a high volume of HTTP requests incoming, or there will be shortly, and then scale down, potentially all the way down to 0, meaning there are no running origins, when it expects that there are going to be fewer HTTP requests, or in the case of 0, when it expects there to be no HTTP requests. Okay, so now we're going to dive into each one, and we will see each of these in code as well. So hold on for that. So first of all, the origin. I alluded to this, but it's really important to remember that in a system, and really any distributed system, but especially in Kubernetes, and even more especially when you're auto-scaling, the origin is not in a stable location. So you can't access an origin, you can't address an origin based on an IP address. You can, with some extra machinery, address an origin based on a DNS name, but you have to know what the DNS name is, and you absolutely cannot rely on the origin to be accessible at any point either. That's what we mean by stable. So it's not accessible by IP because it may move, and it may not be accessible at all, even if you use DNS, because it may not be running at all. And again, also, since it's written by somebody else, you can't rely on any specific amount of uptime. It may run out of memory, it may crash, something else may happen, and we have to account for all of that in our proxy. Often it's good to know that the origin is stateless, again, because the origin can be moved around the cluster a lot more easily then. So possibly good for the app developer that's building the origin, for it to be stateless. But from our perspective on the proxy side, it can actually create more challenges for us because the origin is much more easily moved around the cluster at any point in time. And we mentioned the scaler. That's what we mean by controlled by other software. There is often no manual person or operations team that is creating new replicas or removing replicas of the origin. We need to be aware that the scaler can and will add or remove origin replicas at any time. So the good news is we don't need to have people controlling it. But the challenge comes in that we need to have the proxy aware of the scaler and possibly communicating with the scaler in a reliable way to coordinate how and when it forwards requests. So then there's the scaler. Of course, we talked a little bit about this. It automatically adds and removes origin replicas. It may not predictably do so. And that, of course, is why we need the proxy to communicate with it, and vice versa. Now, of course, we're in a distributed system. The same challenges exist for proxy to scaler communication as they do for any other RPC. The proxy needs to work properly as best as it can, even if it can't access the scaler, and vice versa. So we need to design these things with the best case, the happy path of being able to communicate reliably, but we need to design them such that they still work even if we can't. So a nice way to describe that whole thing is to make the common case easy and make the hard case possible. And then finally, what we're going to focus on today is the proxy. So the proxy is stateless, and that's important to remember. Okay, so not only does that mean the proxy doesn't talk to a database and it doesn't rely on the scaler to store any information about the origins, but it also means that whatever's going on in memory with the proxy should be able to crash, come back, and still pick up and work properly. It may not pick up where it left off, so it may drop requests if the proxy is forcefully shut down, and there's not much we can do about that, but the proxy should continue working properly for new incoming requests if it is started back up after a crash. The proxy handles two incoming events. So one, of course, it acts when there's an incoming HTTP request from the outside, from a client. but also it reacts when it sees that the scaler has changed state. Okay, so it only reacts to state changes. It never stores state or requests a new state. Okay, so a state change that we're talking about here is basically if the scaler reports that it has scaled the origin up or down, the proxy then takes action there. And most importantly, and this is an important concept, an important feature for almost all proxies, is that it needs to handle faults, origin faults. Of course, it needs to handle scalar faults too, and it does it similar way. But primarily, it needs to handle origin faults. What does that mean? It means that it needs to intelligently retry if it can't access the origin. If it can't make a TCP connection to the origin, or it does make a TCP connection, but it hasn't been able to issue the HTTP request, or it was able to issue the HTTP request, but it hasn't received the response yet. Okay, so there are a few different fault domains. The proxy needs to handle all of them intelligently and properly. So before we go look at the code, just going to point out a little bit of the architecture of that code. So for our proxy, we have two major pieces of functionality. We've got a wait queue and we've got the forward component. Okay, so the wait queue occurs first, and this happens before any networking happens at all. So we get an inbound request, and immediately thereafter, we ask the scaler, do you have one or more replicas for the origin that we're trying to forward to? Okay, and it's called wait because the proxy will wait until the scaler says there are one or more replicas. Now, the proxy has to do this reliably. So the proxy has to understand that maybe the scaler won't reply at all. And also, ideally, the proxy needs to do that request quickly. So it needs to ask the scaler, preferably outside of the critical path. So an HTTP request should not be slowed down if a scaler is slow. We won't see that in the code today, but you'll see how it may be possible. And it also needs to quickly move from the wait functionality to the forward functionality. Okay, and it has to do that knowing that something about the origin may change between when it gets the notification from the scaler that there is one or more replicas and when it actually issues the connection down to the origin. Okay, and of course, then the forward functionality is common to many proxies. It has to attempt to issue the connection to the origin, and then it has to forward the HTTP request, and then it has to get the response and return it down to the client. But even more, this all needs to happen in such a way that it can all be canceled if the client, so the incoming HTTP request, if they cancel the request or their connection gets severed. So if we don't do that, there will be one or more Go routines leaked. They'll just be waiting there for something to happen. And then eventually, if they do get a request forwarded down to the origin and they get the response back, then they'll be waiting to return the response down to the client, which no longer exists. And that's why we say we should use the HTTP request context for everything possible in the proxy. And that is to say that anywhere that we wait for something inside the system, so if we wait for the scaler, we wait for the origin, for example, anywhere where we have a chance to cancel or stop making progress, we should always be checking if the context is done. So also, one more point that's important to make here is if we don't wait on the, or if we don't check the context state, we should be checking the state of a context that is derived from the HTTP request context. So let's go into the code. Before I get there, this short link will take you to all the code that I'm going to show here. It's all open source. There are instructions on how to use it. It's MIT licensed, so if you want to take it and use it for your own open source, you're more than welcome to do so. And I'll put this link at the end of the talk as well if you don't want to look at the code now and you want to just follow along here. So I will go over to the editor. And we've got our three components here: origin, proxy, and scalar. PKG just has utilities for us. Slides is the slides, so that's not code at all. So let's see this working in a few different function domains. So we're going to run our proxy in the bottom left. We're going to run our origin in the middle left. And we're going to run our scalar in the bottom right. Run scalar. There we go. So we've got our origin running on port 8080. It's going to contact the scalar, do RPCs to the scalar on 8082. And it's going to forward requests to the origin on 8081. Our origin is here. It just returns hello world, basically. And then our scalar is here. And it's hard-coded at the moment to return that there is one replica of the origin. We can change that, and we will change that and see how that works. But at the moment, this is a simulated scalar that doesn't, obviously, it doesn't manually or automatically change the number of physical origin servers that are running. That would be something that you, of course, would want to do if this was running in Kubernetes. But of course, I don't have time to show all of that today, unfortunately. But let's go and see what happens in the success path. So this is everything is running. The proxy should forward the request all the way down to the origin and then return the response all the way back to me. So we did a request, we got a response back, and inside of the proxy, there's quite a bit of logging. And this is what the logging looks like in the success path. In our origin, we see we got the request for slash. And then here we see the proxy, made a request down to the scalar. The scalar reported one replica back to the proxy. Okay, so that's the success path. Let's go and find out now what happens when the proxy cannot access the scalar. So we've just shut down the scalar. We're going to do our curl again, and we're going to see that the proxy starts waiting. So we've got this thing called an error tolerance inside of the proxy. The proxy will issue requests to the scalar up to X times, and until it reaches an error tolerance, which is just a number of errors that it will accept until it considers the scalar to be unavailable. You can change the way that you handle the error tolerance yourself if you'd like. You can have the proxy not wait for the scalar at all. You can have the proxy check with the scalar once, and if the scalar is not available, you can still just immediately forward the request onward. And there are a couple other ways to handle this as well. But the basic idea is somehow the proxy should check with the scalar if there are replicas. And if there are not replicas, the proxy should indicate to the scalar that it would like some replicas to be created. And after which point the proxy then should forward the request on to the scalar. Okay, so the next failure domain here is, what if we run the scalar and we have 0 replicas? So this is a functioning scalar with 0 replicas available. We're going to run it, and we're going to make a request. So now, same idea, the proxy can connect to the scalar this time though, gets back 0 replicas, and this is where the proxy would issue a request to the scalar saying, I see that you have 0 replicas, please scale up to 1, report back to me when you've done it, and then the proxy, once it gets back the notification that there is 1 or more replicas, then the proxy will issue the request down to the origin. Okay, so let's go back to 1 replica for the scalar, restart the scalar to get 1, and then the final failure domain is let's shut down the origin. So we have a scalar that says there are replicas. For some reason in the system, we don't have any actual replicas though. We're going to issue another request to the proxy. And you see here, we have dialing, try 0, try 1, try 2, and so on and so forth. So this is the proxy getting the notification from the scalar that you are ready to forward the request. But after the proxy gets that notification, something else is wrong. Possibly the network's inaccessible, maybe the origin keeps crashing, whatever it is, this is the proxy being resilient to problems with the origin. And in our case, we've configured the proxy to be very forgiving of origin failures. It will end up retrying, I believe, 100 times, maybe more, and before it fails out and says, requests failed, the origin's unavailable, whatever. But the last piece that we're going to show here is that in all of these failure domains, the retrying will stop if we sever the request, sever the connection from our curl. So if I Control C out here, because we're using that request context all over the place in our retries for the origin and in our retries for the scalar, we stop and we release all of our go-routine and other resources here, just because we are always checking that request context for it to be done. Okay, so now that we have a decent idea of how this works and how it handles failures downstream and upstream, let's go check out the code. So we showed the scalar, very simple HTTP server, just literally responds with 0 or 1, 2, 3, 4, whatever it is. Now this would be a lot more complex, of course, if it was scaling in a more dynamic system than on my machine. This would be not only something that reported the number of replicas, but it would also take action when some inputs happen. So potentially would look at the HTTP request queue on the proxy, and when it reaches different watermarks, it may start automatically scaling up or down. There may be knobs to turn for operators to manually scale up and down as well. And this may not just be a request response. This may be a streaming RPC interface as well, so that proxies can make persistent connections to the scalar, and proxies can get live, up-to-date streaming indications that scaling up and down happened as well. So this, of course, could be much more complex and feature-rich, but for our purposes today, just having an RPC call to get the number of current, fake number of current replicas can show off sort of how we build this whole architecture. So that's the scalar. Origin, very similar. It's just, this is the simulation of the user building an application. This just returns a string, essentially. But the proxy, of course, is where we're going to focus. So starting with main, our general skeleton here is we fetch the URL for the scalar and the URL for the origin, the one that we're trying to forward to. We create our HTTP servmux. We're going to ignore this for just a second. In the servmux, we attach one route. This handler will handle all incoming requests, and of course, we'll proxy them back to the origin. And then we just set up the server and start listening on our proxy port 8080. So then diving into here, we've got our forwarding functionality here. So forwarding is not only forwarding HTTP, but we set up a dialer. So a net.dialer, we literally wrap the net.dialer in another net.dialer that we've built that does retries. So if we go into here, you can see here, this is a very basic backoff functionality. So we pass our core net.dialer, that was here. It's set up with a connection timeout and a keep alive time. We can configure this a lot more if we want to, but these are the basic two important timeouts to be aware of. And we pass this dialer in to here. Now this thing returns a dial context function, okay? So the dial context function looks like this. Takes in a context, takes in a network type, so almost always going to be TCP in our case. And then it takes in the address that we're trying to issue the connection to. And it returns a net.con and an error. Now, this interface is what our built-in HTTP reverse proxy requires, and we'll see that shortly. So we made this dial context func type ourselves, but it happens to match the exact interface, the exact function parameters and return types, that is, that are reverse proxy type, which is from the standard library, what that requires. So we're returning that function. This for loop is doing our retries, and we're just doing our backoff here. So we take the actual net.dialer function, the net.dialer struct that was passed in. We call our dial context function. And again, this is passing the HTTP request context all the way down, even inside of the standard library. So this function, of course, will return an error if the context is done, such as when someone Control-Cs on a curl request. We check to see if the dial succeeded. If it did, then we return the resultant connection. And otherwise, we back off. Now, you could do exponential backoff here. You could do other intelligent backoff strategies. I haven't done that here to keep the code a little bit cleaner, but this is the general idea. So we create a timer. We select over either the timer channel here, in which case we're just going to try the next iteration of the loop, or we're going to stop if we're at the last iteration of the loop. And otherwise, if the context is done, that's an error. We time out. So that is the forwarding part of this. Now, the other part is the wait part. That's here. So we've got this thing called a scalar forward wait func. So going into here, we've got this proxy forward wait func, takes in a context and returns an error. Now, all this is it's called inside of the proxy, passes, again, that HTTP request context, returns nil if we're done waiting and ready to try to issue the request to the origin, and returns a non-nil error if something is wrong and you should not. So if the wait failed for some reason, and you should not forward the request back to the origin. Now, inside of here, again, we've got a for loop. Again, we're just doing a linear backoff. We're not doing exponential. We just back off every time we need to back off if there was a failure or something along those lines. We basically just call a function called wait like this, and we just wait the same amount of time each time, basically, each time there's a failure. We also have a thing called an error tolerance. So, of course, you can see every time we try to get the number of replicas from the scalar, or we try to decode the request, those all come with errors, as we all know. And we want to have an error tolerance. So, for example, if we try to get the number of replicas from the scalar, and we get an error with making a network connection to the scalar, let's say, we want to have a tolerance for that. And what the tolerance essentially is just a sheer number of errors we've seen so far in our for loop. If we reach that tolerance, then we want to exit out of this entire function and return a non-nil error. Now, every time you see a call to tolerance met, you also see a corresponding proxy.wait. So this tolerance met function is just a little convenience function that will return either true or false. If it returns true, then we've met our error tolerance and we need to return a non-nil error. Otherwise, we need to do a wait. Now, this wait function will be very, very familiar to the previous one, the forward functionality. Create a timer, return nil if we reach the timer, return the context error if we did not reach the timer and the context was closed beforehand, before we reached the timer. So really, that's the pattern here. Make our request to the scalar, try to decode it, we'll try to read the body of it, try to decode it into an integer, and then basically you get a number of scaled. That's the response body. If you have more than 0, meaning you have one or more replicas, you're done. Return a nil error. Otherwise, if you don't have that, if you have 0 replicas, we want to wait, just the same as if we got an error and we hadn't met the error tolerance. Once we are done with the wait, if the wait returned an error, that means that the context was done and we return our error. Otherwise, we're just going to go back up to here. Now, this is going to loop forever. That's different than the number of retries from our forwarding. This will loop forever. It will attempt to loop forever. Of course, it won't loop forever because the context because of this timeout right here. Or more likely the context may time out as well. So now we've covered our forwarding, we've covered our waiting, and now we put them together with our HTTP handler. So in here, fairly straightforward on how we use this, although there is a lot of code. Create a new context derived from the request context. So that's a context that will time out based on a timeout that we've passed in. That's a global timeout for the request. So we are going to time out everything, whether we're waiting for the scaler, whether we're trying to forward and waiting for a connection, whatever else it is. If this wait timeout has passed, we just stop everything. Now, we have our wait func here, and I have actually chosen to do the wait func inside of an error group. Now, this is not strictly necessary, but I find that it is very useful to use an error group here, and not just, of course, the alternative is to just call wait func directly. You would check the error on this as well, and you'd return the error and so on and so forth. But you may find, you likely will find in your proxy that you may want to wait on other events as well. Okay? And in that case, you would have a second group.go. You would have something else. Wait for something else. And in fact, I did in the Kubernetes production one that I did inside of the KEDA project, that's exactly what happened. So I actually left the error group here on purpose because you may find yourself having a second thing that you may wait on, or a third thing you may wait on, or a fourth thing, and so on and so forth. And it happens to be very convenient to just do grp.go or errorgroup.go and add another condition that you may want to wait for. Okay, so that's really this part right here. All of this code, we're doing our wait. Okay, so once we exit our wait, assuming that we did not have an error on the wait, so in the happy path, we go from wait into forward. Now forward, we've moved that out to a separate function. And this is where we create our standard library single host reverse proxy, where basically we're using the httputil standard library functionality, and we're doing a reverse proxy, but we're doing the reverse proxy in such a way that we're resilient to the origin failing in some way, even after the scaler reported that there is one or more replicas of the origin. And that is this right here, this dial context func. Okay, so this is the dial context func that we saw over here that had the number of retries and it had the backoff and so on. We've just passed it. We've passed it in here as this dial context func function interface. And as I remind you, that function interface is what our HTTP transport expects. And we take this HTTP transport and we put it into our proxy round tripper right here. So all this is to say that when the proxy receives an incoming request, it will call this dial context func to try to issue the connection to the origin. And once this dial context func returns, if it returns a nil error, then it will proceed to forward the request down to the origin. Of course, if it doesn't return a non-nil error, if it returns a non-nil error, then it will fail and it will execute this error handler, which will return a 502 down to the client. The last piece of it is if it is a nil error, then it proceeds to call this code. This is called the Proxy Director. All we're doing here is we are taking the incoming request from the client, we're doing a few rewrites to it, such that the origin gets passed a few pieces of information that are pertinent to the client, to the curl in our case. But also the request is written so that it actually gets forwarded to the origin, the right URL, the right host. We preserve the path and we preserve the query string. And there's a few other things that we could do in here, but this is the bare minimum that we need to. So finally at the bottom here, if you are unfamiliar with reverse proxies in the standard library, they themselves are an HTTP handler. So we can just call serve HTTP and be done with it. Serve HTTP is fairly complex, but essentially what it does is takes the incoming request, R, tries to dial. If it does dial successfully, we do this. If it doesn't dial successfully, we do this. If it does a successful dial, and after this happens, then it issues the new HTTP request after this function was called down to the origin. The origin returns the response, and it literally just pipes the response back through this W, HTTP response writer, all the way down to the initial client. So that is essentially all of it. Now, there's a lot more you can do. Like I mentioned, you can speed up the wait step. This wait step can happen from a cache in memory, for example. There's a lot more you can do here. But starting from this foundation, you'll find that you can build a fairly robust system just with an error group, a little bit of waiting, a couple for loops, and don't forget to rely on that context. So if you do go and build your own, remember that this concept, the wait step and the forward step and the concepts that we saw inside of the code, this is all applicable outside of Kubernetes. So if you need to proxy something, you are running in a distributed system, and these concepts will be applicable outside of Kubernetes. Remember that the error group, especially, that happens inside of Go routines. So you have to remember, not only with your timeouts, you have to remember to look at your context, but you have to remember to pass the context into the error group as well, because that happens in Go routines too. Two other pieces, and I've alluded to both of these as well. You want to keep your proxy as stateless as possible. Don't put the status of requests inside of a database, for example. You want the proxy to be able to crash and start back up and function properly, regardless of how it crashed, regardless of what state it was in when it crashed. And then finally, I alluded to this as well, but you want your RPC calls to be as simple as possible and as few as possible. And that's for two reasons. One, of course, is you don't want to slow down requests coming from clients. You want them to go as quickly through the proxy and out to the origin, and then as quickly back from the origin through the proxy to the client. You want all that to happen as quickly as possible. But also, the more RPC calls you make, the more code you need to write to handle failure domains. Because assume that any RPC call can fail. You need to assume that in Kubernetes, really inside of any distributed system. So with that, I want to say thank you again. You can grab the code from here, the demo code. The demo code has a link to KEDA and this specific, the specific code that this code was inspired from. I really encourage you to go check that out. File issues on it if you have questions. I'm more than happy to talk about it. A few places that I live in the internet, and this is also my handle in the Gopher Slack, so you can feel free to DM me. I would love to chat about this stuff as well. I also live code this project as well as a few other Go projects on Twitch every Monday and some Fridays, so really encourage you to go and check me out there. That's a shameless plug. So I'd love to take questions live here as well. I think feel free to put them in chat. There may be a better way, so I'll leave that to the organizers to tell you. But otherwise, thank you again so much for coming. I really enjoyed this, and I will hope to talk to you soon. Take care, everybody. Hello, everybody, if you can see us.
I definitely can see you on the screen. Yay! We are live. Great. Okay, so we had some discussion in chat about operator SDK and what other name of the project. What was that? Yeah, Kubil. What's that and what's the difference between them?
Yeah, they're very similar. So I don't know all the history of it, but they're both they both do more than just code generation. But you start with the tooling that they give you, and you generate all the code for your operator from sort of a definition language. So I'm more familiar with KubeBuilder, And in that case, you build a struct or structs for your custom resources in Kubernetes. You run their tooling through, and it'll generate not only the YAML definitions for it, but it'll also generate the stubs to run your operator in production. Then the other side is that it provides all the libraries for the event loops and caches and notifications that come in when a Kubernetes event comes through that you are interested in. And really, in most cases, you fill in one method in Go, and you have a fairly full-featured controller. So, for example, the first controller, the first version of the controller that we built for the HTTP service, it took a day and a half of coding to get something very reliable. It can crash, and it did. It crashed quite a bit the first implementation. They can crash and come back and recover from those issues. And yeah, I would highly recommend using one of those two projects if you're thinking of building a controller. And I have built controllers from scratch before either of these projects, and it's much easier to use one of those two systems to build your controller for you. But they're very similar. So I would say KubeBuilder is more of, it's sponsored by a special interest group in Kubernetes. I think it's setting more of the standard for how to build controllers. And Operator SDK is the same. It's the same style. It's very similar technology. My personal opinion, though, is KubeBuilder, just because it's backed by the special interest group. So it feels a little bit more official, I suppose. But of course, that's my personal opinion.
And Operator SDK is sponsored by Red Hat, I think, right?
Yeah. So it's certainly still well supported and actively developed and so forth. So it's a good point. Yeah.
Okay, let's see if we have some other question. Looks like no. Fun question. You mentioned that you like to make pizza from scratch.
Yeah.
Do you also use Scratch as a base image for your Docker containers?
Let me check. It's a gcr.io image. I can't remember exactly what it's called. I'll put the link in here. Distroless. I'll put it in the chat. It's the Docker file for the HTTP operator.
Nice.
Yeah.
Okay.
Sometimes I'm lazy, though. I should mention this. Sometimes I'm lazy and I just use the Ubuntu image just to full transparency there.
Yeah. Many of us would just don't admit it.
Yeah, I'll admit it. It's fine.
Yeah. Okay. Thank you very much. We'll do the closing now, but again, it was a pleasure to have you.
Yeah. Thank you so much, everybody. This was wonderful. I really appreciate it.
Thank you.
Bye.